the silence that hides the danger. Out there in the void, in the cold, endless darkness between stars, danger lurks in silence. No warning, no sound, no glow. Just a flash, a ripple, a burst, and everything could change. We live on a fragile blue planet, protected by a thin atmosphere and an even thinner sense of security. Most people look at the night sky and see beauty, but astronomers see more. They see motion, force, energy, and threats. Invisible threats. What if, at this very moment, a high-energy gamma-ray burst is heading toward Earth? What if an ancient black hole, undetected, is drifting closer than we think? What if solar storms or cosmic radiation are already affecting life without us even knowing? In this documentary, we explore the hidden dangers of space, the threats we can't see, can't touch but can measure. From distant cosmic events to silent particles passing through your body every second, we ask one critical question. Are we really safe in the cosmos? Or is our world more fragile than we imagine? A universe full of energy. Space is not empty. It's a dynamic, chaotic ocean of particles, radiation, and gravitational forces. Though our senses perceive the vacuum as serene and still, the universe is alive with energy, most of it invisible to the human eye. Our planet is constantly bombarded by particles from space neutrinos, cosmic rays, solar wind. Every second, trillions of neutrinos pass through your body without leaving a trace. They come from the sun, from stars, from events billions of light years away. But not all cosmic visitors are so gentle. From the most violent events in the cosmos come some of the most dangerous forces. Gamma-ray bursts, magnetar flares, rogue black holes, high-energy cosmic rays, and coronal mass ejections are just a few of the phenomena that could impact Earth, some catastrophically. Gamma-ray bursts, the silent apocalypse. Gamma-ray bursts GURBS are the most powerful explosions in the universe. When massive stars collapse or neutron stars collide, they can release narrow beams of gamma radiation traveling near the speed of light. If Earth happens to be in the path of one of these beams, the effects could be devastating. GURBS can strip away our atmosphere, destroy the ozone layer, and expose the surface to deadly ultraviolet and cosmic radiation. Mass extinctions on Earth, like the Ordovician extinction, may have been triggered by such events. The terrifying part, GURBS happen all the time. Most are far enough not to hurt us. But a close one, even from 6,000 light years away, could be catastrophic, and we would never see it coming. Rogue black holes, the invisible travelers. Black holes are often portrayed as monsters in science fiction, but real black holes are even stranger and more elusive. Most black holes are born in supernova explosions and remain in place, quietly distorting space around them. But some are moving. Rogue black holes, kicked out of galaxies by gravitational interactions or collisions, wander the universe invisible, undetectable by light. If a stellar mass black hole passed near our solar system, it could disrupt planetary orbits or slingshot comets into Earth's path. If it came closer, it could strip Earth from the sun, or worse. There may be millions of these dark wanderers out there. We don't know where they are. We don't know if they're coming. Solar flares and coronal mass ejections. While distant space poses serious threats, our own sun is no less dangerous. Solar flares and coronal mass ejections, CMEs, are eruptions of charged particles from the sun's surface. When they hit Earth, They interact with our magnetic field, producing beautiful auroras and chaos. The Carrington event of 1859 was the most powerful geomagnetic storm ever recorded. Telegraph systems failed, sparks flew from wires, and northern lights were visible in the Caribbean. Today, a similar storm could disable satellites, damage power grids, disrupt communications, and affect navigation systems worldwide. The economic and social impact would be massive and global. And the sun is becoming more active. Cosmic rays and DNA damage. High-energy cosmic rays originating from distant galaxies or unknown sources strike Earth constantly. While our atmosphere and magnetic field shield us from most, astronauts in space and airline crews at high altitudes are exposed to more. Cosmic rays can break DNA strands, cause mutations, and increase cancer risks. Over long timescales, they may even influence evolution. During solar storms, radiation levels rise dramatically, making deep space travel hazardous for future astronauts. Mars, with no magnetic field, is bombarded constantly. Understanding and shielding from cosmic radiation is a key challenge for interplanetary exploration. Supernova galactic shockwaves. When a massive star dies, it explodes in a supernova, blasting heavy elements and radiation across space. If one happened within 50 light-years of Earth, it could destroy the ozone layer, cause climate shifts, and trigger extinction events. There's evidence that supernovae have impacted Earth in the past. Layers of iron-60 found in ocean sediments suggest a nearby explosion just a few million years ago. Betelgeuse, a red supergiant 642 light-years away, is expected to go supernova, not close enough to harm us, but a stark reminder of the potential power of stellar death. Micrometeoroids and high-velocity debris. Every day, Earth is hit by over 100 tons of dust and micrometeoroids. Most burn up in the atmosphere, but in space, these tiny particles can cause serious damage. At orbital speeds, even a grain of sand becomes a bullet. The International Space Station is armored to protect against such impacts, and satellites are often damaged or destroyed by debris. Micrometeoroid storms, clouds of high-speed dust left by comets, can intensify the threat. A large burst could disable key satellites, or even threaten future space habitats. Neutrinos, the ghost particles. Trillions of neutrinos pass through you every second. They rarely interact with matter, but they come from nuclear reactions in the sun, supernova, and the early universe. They're harmless to us now, but studying them could reveal hidden threats. Sudden increases in neutrino flux could signal a supernova before it becomes visible, acting as an early warning system for cosmic disaster. Psychological impact of cosmic fragility. Understanding how vulnerable our planet is can change how we see the world. Space isn't hostile because it hates us, it's indifferent. The universe is not designed for us. We are a fragile pocket of order in a chaotic system. For some, this is terrifying. For others, it's empowering. Knowing the risks allows us to prepare, to adapt, and to innovate. The more we understand space, the more we understand ourselves. How we protect ourselves now and in the future. Despite the risks, we are not helpless. Satellite shielding, early warning systems for solar flares, space weather forecasting, protective habitats for astronauts, nuclear-powered probes to monitor cosmic events. Future ideas include magnetic shields, deep underground bunkers, and even planetary deflection systems. The key is awareness and readiness. Should we be worried? The universe is dangerous, but so is life itself. Most threats are low probability, but high consequence. Understanding them helps us reduce risk. Many scientists are working to model, monitor, and predict cosmic hazards, and humanity has never been more prepared. The biggest threat is not knowing. The fragile miracle of Earth. We live on a miracle, a warm, wet, shielded world in the universe that is mostly empty, cold, and dangerous. Invisible threats surround us. But we're learning, watching, listening, building, and maybe, just maybe, that knowledge is our greatest shield. If this video opened your eyes to the power and fragility of spaceflight, subscribe and share it with someone who thinks the night sky is peaceful. Because out there, it's not silent. What happens when two galaxies collide? The fate of the Milky Way and Andromeda. A cosmic dance of destruction and creation. Galaxies are not static islands floating peacefully in the universe. Instead, they move, interact, and at times, crash into each other in spectacular cosmic scale collisions. Our Milky Way is no exception. In about 4.5 billion years, it will have a fateful encounter with its closest large neighbor, the Andromeda Galaxy M31. The two galaxies, each containing hundreds of billions of stars, will merge in a dramatic event that will reshape the entire local cosmic landscape. But what exactly happens when two galaxies collide? Does it mean total annihilation? What will happen to the Sun and our solar system? Could this collision trigger the formation of new stars and black holes? And could such a process already be occurring elsewhere in the universe? Let's embark on a journey into the far future and explore the breathtaking science behind galactic collisions. The collision course. How do galaxies move? Galaxies are not stationary. They move through space, driven by the expansion of the universe and gravitational interactions with neighboring structures. The Andromeda Galaxy is currently about 2.5 million light-years away from the Milky Way. However, it is moving toward us at a speed of 110 kilometers per second, 68 miles per second. Why is Andromeda moving toward us? Unlike most galaxies that are receding from us due to cosmic expansion, Andromeda and the Milky Way are gravitationally bound within the local group, a cluster of over 50 galaxies. The gravitational attraction between these two massive spirals is stronger than the expansion of space between them, pulling them closer together. The timeline of the collision. In about 2 billion years, Andromeda will start appearing much larger in the night sky as it approaches. In 3.8 billion years, the first close encounter will begin, stretching both galaxies due to tidal forces. In 4.5-5 billion years, the merger will be nearly complete, forming a single giant elliptical galaxy, sometimes referred to as Milkomeda or Milkdromeda. Will this be catastrophic for our solar system? Let's find out. What happens to stars and planets? When two galaxies collide, Individual stars do not typically crash into one another. This is because space within galaxies is mostly empty. The vast distances between stars make direct collisions incredibly rare. However, the gravitational chaos from the merger will have profound effects on the structure of both galaxies. Effects on the stars. Stars will be gravitationally disturbed, flung into new orbits, and some may be ejected entirely into intergalactic space. The central supermassive black holes of both galaxies, each weighing millions of times the Sun's mass, will spiral toward each other and eventually merge. Massive shockwaves from the collision will compress gas clouds, triggering a new wave of star formation. Effects on the solar system. Our Sun will likely survive the collision, but its position within the galaxy will be altered. The solar system could be pushed into the outer halo of the newly merged galaxy. It could also be ejected entirely from the galaxy, drifting through intergalactic space. By this time, 5 billion years from now, the Sun will be nearing the end of its life, becoming a red giant, engulfing the inner planets, including Earth. So while humanity might not exist to witness it, the fate of our cosmic home is sealed in this grand encounter. The birth of new stars and the rise of black holes. Galactic collisions lead to enormous bursts of star formation, known as starburst events. When gas-rich galaxies merge, their clouds of hydrogen are compressed, igniting the formation of millions of new stars. Formation of supermassive stars. Massive young stars will form at an accelerated rate. Many of these will burn out quickly, leading to spectacular supernova explosions. The growth of black holes. Both the Milky Way and Andromeda contain supermassive black holes at their centers. When the galaxies merge, their black holes will spiral toward each other, eventually combining into a single, even more massive black hole. This process will unleash gravitational waves, ripples in spacetime first predicted by Einstein and confirmed by LIGO in 2015. Galactic mergers across the universe. Colliding galaxies are not uncommon. Astronomers have observed many such events across the universe. Here are some famous examples. 1. The antennae galaxies. Two spiral galaxies in the process of merging, showing massive bursts of new star formation. 2. The Whirlpool Galaxy M51. A classic example of a smaller galaxy being absorbed by a larger spiral. 3. NGC 6240. A violent merger between two galaxies with dual supermassive black holes. These examples help scientists predict what might happen when the Milky Way and Andromeda eventually collide. The final outcome: what will the new galaxy look like? After several billion years of gravitational chaos, the two galaxies will finally settle into a new form. The final product will likely be an elliptical galaxy, with most of the distinct spiral structures erased. This new galaxy, Milkomeda, will be one of the dominant galaxies in the local group. It will have a larger and more active central black hole, potentially making it one of the most energetic galaxies in the region. Should we be concerned? The collision of the Milky Way and Andromeda is an inevitable part of cosmic evolution. However, humanity will likely not exist by the time this event unfolds. If advanced civilizations still exist by then, they might observe the merger with awe rather than fear. In the grand scheme of the universe, Galactic collisions are essential for its evolution. They lead to the formation of new stars, the growth of black holes, and the continuous reshaping of the cosmos. So, the next time you look up at the night sky, remember, the dance of galaxies is ongoing, and one day, our Milky Way will become part of something even greater. Like this video? Subscribe for more mind-blowing space content.
When we look up into the night sky, we are struck by the enormity of the universe. There are about 100 billion stars in the Milky Way, and beyond it there are trillions more galaxies, each containing billions of stars and perhaps trillions of planets. Amidst this cosmic splendor, the question arises, if life in the universe is so possible, why do we see no signs of it? This question is known as the Fermi paradox, and it remains one of the most intriguing mysteries of modern science. Over the past decades, mankind has made many attempts to find extraterrestrial signals. For example, the Arecibo message project sent a powerful radio signal to the M13 star cluster in 1974, and in 1977 the mysterious WAD signal was registered, the origin of which is still unclear. The origins of the paradox. The paradox is named after the Italian physicist Enrico Fermi. Legend has it that while discussing the possibility of extraterrestrial life with colleagues in 1950, he suddenly asked the question, "Where is everyone?" That question became the starting point for a host of studies and hypotheses. Since then, scientists have proposed dozens of possible explanations. Some hypotheses are based on the assumption that we haven't yet found the right way to look, while others are based on the idea that life in the universe may be extremely rare. Drake and the Drake equation. An important tool in the discussion of the Fermi paradox has been the Drake equation, proposed by astronomer Frank Drake in 1961. This equation attempts to estimate the number of civilizations in our galaxy that we could make contact with. The formula takes into account the rate of star formation, the fraction of stars with planets. The Kepler and TESS studies have shown that almost every star has at least one planet. The number of planets suitable for life. The probability of life arising on those planets. The probability of intelligent life evolving. The duration of technological civilizations. While the exact values for most parameters remain unknown, even optimistic estimates indicate that there must be hundreds or thousands of civilizations in the universe. But where are they? Possible explanations. 1. We are alone. One of the most radical options is that life is extremely rare. Earth could be a unique place where all the conditions for the origin of life were perfect. This explanation is controversial because it contradicts the assumption that the universe is large enough that life could have arisen in other places. 2. The problem of scale. Another answer lies in the vast distances between stars. Even if intelligent civilizations exist, they may be too far away to make contact. Radio signals travel at the speed of light, and even the nearest stars are light years away. This creates a problem not only in transmitting messages, but also in receiving them. 3. We are looking the wrong way. Current methods of searching for extraterrestrial life focus on radio astronomy. However, civilizations may be using technologies that are unknown to us. For example, they may use quantum entanglement or forms of communication that we cannot detect. 4. Dark forest. This hypothesis, proposed by writer Liu Cixin in his novel The Three-Body Problem, suggests that intelligent civilizations deliberately avoid contact for fear of being destroyed. The dark forest reflects the concept that each civilization perceives others as a potential threat, which draws a parallel to earthly conflicts where fear of the unknown often leads to isolation or aggression. According to this theory, the cosmos is a dark forest where each civilization hides in order to survive. 5. They are already here. Some hypotheses suggest that extraterrestrial civilizations have already visited Earth, but either left no visible traces or we didn't recognize them. This includes ideas about ancient aliens and unrecognized phenomena. 6. The Great Filter. The concept of the Great Filter suggests that there are stages in the development of life that are extremely difficult to overcome. This could be the origin of life or the development of technology. If the Great Filter is ahead of us, it could mean that our civilization is also doomed. 7. We are too young. Human civilization has only been around for a few thousand years, and radio astronomy for less than a century. On a cosmic scale, this is a negligible amount of time. Perhaps other civilizations have already disappeared, and we are only at the beginning of our journey. The role of technology. Modern technologies such as the James Webb Telescope, the SETI project, and the Breakthrough Listen initiative are already exploring millions of star systems to look for unusual signals and possible signs of extraterrestrial life. So far, however, all attempts have not yielded tangible results. Interesting fact: radio signals sent from Earth have already reached a radius of 100 light-years, covering several hundred star systems. However, the likelihood of an extraterrestrial civilization catching them at this very moment is extremely low. The Fermi paradox is not only a scientific mystery, but also a philosophical challenge. It forces us to think about our uniqueness, our future, and our responsibility to the planet. If we are truly alone, it imposes an enormous responsibility for the preservation of life. The Fermi paradox remains an open question that inspires scientists, philosophers, and space enthusiasts to search for answers. Perhaps the solution lies in the future, or perhaps we are simply not yet ready to understand it. For now, the cosmos continues to be a great mystery, reminding us how big and mysterious our place in it is. My opinion about the Fermi paradox can be formulated as follows: it is not just a scientific mystery, but also a philosophical challenge for mankind. It forces us to think about our place in the universe, about whether we are unique or simply do not know how to look for others correctly. The paradox reminds us how small we are before the scale of the cosmos and how much we don't yet understand. One of the most intriguing explanations, U201 for the dark forest, suggests that intelligent civilizations avoid contact because of fear. This evokes parallels with human behavior on Earth, where fear of the unknown is often the cause of conflict. Perhaps the solution to the paradox lies in the development of not only technology, but also our own understanding of each other and the universe. Ultimately, the Fermi paradox is an incentive for us to keep exploring, asking hard questions, and searching for answers. Even if we never find others, the very process of searching makes us more aware, inquisitive, and ready for future discoveries. After all, it is in trying to understand the unknown that the real magic of science is revealed.
Hello to all astronomy enthusiasts. Today we're going to talk about mankind's incredible journey to find new worlds, exoplanets, planets outside the solar system. Scientists have discovered thousands of exoplanets in recent decades, and each one reveals something new about our universe. But how do they find them? What methods do they use to see planets tens or even hundreds of light years away? We'll talk about the most effective and surprising methods astronomers use to find exoplanets. What are exoplanets, and why are they so important? Exoplanets are planets that orbit stars outside of our solar system. These celestial bodies are of particular interest to scientists because they can answer the question, are we alone in the universe? By studying exoplanets, we can understand whether other parts of space have conditions for life similar to those on Earth. Moreover, the search for exoplanets expands our understanding of the formation of planetary systems. The main challenges in the search for exoplanets. One of the main problems is that exoplanets are extremely difficult to see directly because they reflect very little light from their stars and are virtually invisible against their bright light. It's like trying to see a firefly next to a powerful spotlight at a great distance. Therefore, to search for exoplanets, scientists are developing methods that allow you to notice not the planets themselves, but their influence on the star or the light passing through their atmosphere. The transit method. The method of transits is the most common and effective way to detect exoplanets. When a planet passes between its star and Earth, it partially blocks the star's light, and its brightness drops slightly. These small changes in brightness observed by telescopes allow scientists to determine not only the presence of the planet, but also its size, orbital period, and even the density of its atmosphere. How it works. A space telescope observes a star and detects tiny changes in its brightness. If periodic dips in brightness are repeated, this can indicate the presence of an exoplanet passing in front of the star. Examples of the method's use. The Kepler Space Telescope has discovered thousands of exoplanets using the transiting method. TESS Transiting Exoplanet Survey Satellite continues its work by observing bright stars in search of transits. Radial velocity method, Doppler method. The radial velocity method is based on the Doppler effect. When an exoplanet orbits its star, it slightly nudges the star, causing it to shift slightly in space. This oscillating motion causes small changes in the wavelength of the star's light. As the star moves toward us, the light shifts toward the blue spectrum, and as it moves away, it shifts toward the red spectrum. How it works. Telescopes analyze a star's spectrum for changes in wavelengths. If periodic changes occur, it may indicate the influence of a planet orbiting the star. Interesting facts. This method was one of the first ways to search for exoplanets and was a breakthrough in astronomy. One of the most famous examples is the discovery of the first exoplanet around a Sun-like star, 51 Pegasus b in 1995. Microlensing method. The gravitational microlensing method is based on Einstein's theory that massive objects can bend space and time around them, causing light to focus. If a planet passes in front of a distant star, its gravity can temporarily amplify the light from the star, creating a lensing effect. How it works. Telescopes detect sudden flashes of a star's brightness when a massive object passes in front of it. This method is particularly useful for finding planets at significant distances from Earth and can detect planets with orbital periods of tens of years. Examples of success. The OGLE Optical Gravitational Lensing Experiment program uses the microlensing method to search for exoplanets, especially those far outside our galaxy. Direct imaging. The direct imaging method is one of the most difficult but unique ways to detect exoplanets. Here, scientists try to see an exoplanet by blocking the light of a star with special coronagraphs to pick out the faint light from the planet. How it works. Special equipment reduces the brightness of the star's light, allowing nearby objects to be seen. Infrared telescopes, such as the Gemini Planet Imager, can detect the light emitted by the planet and observe it in high resolution. Features out of the method. Direct imaging is used for planets at great distances from their stars, such as young gas giants. The James Webb Telescope can also make important direct imaging discoveries with its powerful infrared instruments. Atmospheric spectroscopy. Once exoplanets are discovered, scientists analyze the composition of their atmospheres to determine if there are traces there that indicate the possibility of life. Spectroscopy is a technique that allows light traveling through a planet's atmosphere to be split into different wavelengths, determining which elements and molecules are present in the atmosphere. How it works. When a planet passes in front of its star, some of its light passes through the planet's atmosphere. Scientists analyze which wavelengths are absorbed by the atmosphere, allowing them to determine its composition. Why it matters. The presence of molecules, such as oxygen, methane, or carbon dioxide, can indicate biological activity or potential conditions for life. The James Webb Space Telescope will play a key role in this line of research. Space missions to search for exoplanets. Space missions are an important part of the search for exoplanets. Over the years, NASA, ESA, and other agencies have launched telescopes specifically designed to discover new worlds. Let's discuss some of them. Kepler, launched in 2009, and has discovered thousands of exoplanets, changing our understanding of the universe. TESS, successor to Kepler, aims to find planets in bright and close stars. James Webb Space Telescope, with its unique infrared capabilities, explores the atmospheres of exoplanets to find potentially habitable worlds. Future missions and search prospects. In the coming years, astronomers plan to make even more progress in the search for exoplanets with new space missions and ground-based telescopes. Plato ESA, focused on finding Earth-like planets in habitable zones. LOVOIR and HABEX NASA, future telescopes that will allow the direct study of exoplanets and the detailed study of their atmospheres. The search for exoplanets is one of the most exciting areas of modern astronomy. It not only expands our knowledge of the universe, but also brings us closer to answering the question of whether there are other worlds like ours. With each new discovery, we get closer to unraveling the mystery of life in the universe. If you enjoyed this video, don't forget to subscribe so you don't miss new exciting stories about the universe and its mysteries.